All right. Good morning, everybody. Happy Thursday. All right. So, so please, I need your attention today. I'm gonna have the best ever review. That's my goal, at least. Okay, that you can have for exam 4B and the final exam. Okay. So, but what I mean by the final exam is I'm not going to be including exam 4B review on the final reviewing when we do reviewing next week because next week is just reviewing. Okay. But today we will be covering, your exam 4B stuff. Like mainly I'll be focusing on the ionic compounds. That's the first thing we did for exam 4B that we tend to forget. And then we will include some of the reactions as well to have fun with. Okay. That's going to be the goal. And the idea is to do our best in tomorrow's exam and also 1 week from tomorrow, which is our final exam, to finish the semester strong. That's going to be the main goal. Okay. I'm going to do my best. I want you to do your best, meaning if you want to use your phone, please use your phone later after this class. Or, please, I just want you to pay attention for your own sake. Okay. All right. Any questions, concerns, comments before we begin? I'm going to start with these two questions. These two questions were in the Tuesday's lecture that I promised to go back to, which I failed. So I'm going to include I removed those two questions from Tuesday's lecture and included them here so that we can complete them today. And then once we're done with these two, then we will move to our review. Okay. All right. Let's take a minute and complete this. I'll open both of them maybe. Go ahead. Meaning we can move on. I'm going to close this question in 5, 4, 3, 2, and 1. All right, PS, let's do this. So here are our responses. Let me clear my doodling first. Okay. So most of us said the limiting reactant is H2, which is correct. Why? We have P4 in excess. And then energy diagram, we are going from AA bonds. What is that? Okay. We are going from AA bonds on the reactant side because we are reacting P4 with H2 to produce PH3. We have AA bonds on the reactant side, AA, which are weaker. And then we have all AB bonds, which are polar and stronger on the reactant side, meaning it's going to have a lower potential energy on the product side. Meaning we're going from higher potential energy to lower potential energy. Therefore, it's an exothermic reaction. Okay. Therefore, the correct answer must be option C. Okay, please, one more time, never select options B and D. The reason is we always go from reactants to products, not the other way around. And A is incorrect because in A, products have a higher potential energy. It cannot be because we have stronger bonds on the product side, meaning lower potential energy must be with the products. Okay. So correct answer is option C for that reason. Let me check the other one. Most of us selected, 87. I need to talk about that. I'll come back to it. And the effect on reaction rate of increasing hydrogen. Okay. Most of us say the rate increases. Okay. Which is great. Okay. So hydrogen, just like P4 is a reactant. Whenever we increase the concentration of that, whenever we increase the number of particles, you're going to have more collisions. More collisions means higher collision frequency. Higher collision frequency means what? Faster rate, faster reaction. Okay, that's it. Now that is about that. And then what about P4? Okay, so P4 again, effect on the reaction rate of decreasing P4. Most of us said reaction rate decreases. That is correct as well. It's the same thing. Okay. So remember, it doesn't matter whether it is limiting or not, or is in excess. Whenever we increase the reactant concentration, it's going to increase the rate. Why? More particles means more collisions per given time, meaning higher collision frequency, meaning higher rate. Okay. Please keep that in mind. Doesn't matter whether it is limiting or not. Okay. Whenever you increase the particles or concentration of the particles or whatever, not whatever, reactants, okay, then it's going to increase the rate. Why? There's going to be a higher collision frequency. Yeah. All right. Now, and then the other way around is true as well. If you decrease the concentration, the rate should decrease. Why? The collision frequency decreases because there will be less collisions per given time. Okay, that's why most of us said rate decreases when you decrease the P4 concentration. And the effect of adding a catalyst, okay, most of us said rate increases. That's what catalysts are for, right? Catalysts are there to increase the rate by decreasing the activation energy. So, that's the main purpose of that. That's the only reason why anyone would add a catalyst for any reaction. All right, the final question is about the stoichiometry of stoichiometric coefficient. Did I say that? Yeah, stoichiometric coefficient of hydrogen. It's about balancing the equation. We have 4 phosphorus on the reactant side. We only have 1 here. Therefore, I'm going to multiply this by 4. Now we have 4 phosphorus on the product side as well. And now we have 12 hydrogens in total on the product side, but only 2 here. So I'm going to multiply this by 6. And therefore, the stoichiometric coefficient of hydrogen is 6. That's it. Done. All right. Questions, concerns, comments do we have? Anything? Any questions, concerns, comments? Anything, please? If there's anything that is not clear, please ask. I don't want anything hanging today, okay? I want everything to be clarified. Okay. All right, I'll reopen the question in case somebody wants to revise their answers. But please, if you have any questions, ask learning assistants or your neighbors or, worst case scenario, me. I really want you to do that. All right. Anyway, let's try this question. I don't know why there is a timer for this question. I did not intend to have that, but that's okay. If you want to make notes, go ahead and make notes. Oh yeah, we need the balanced chemical reaction for this in case you don't have to know the products. I'm going to give that to you. So CH4 reacts with O2 to produce CO2 and H2O. Okay, we have 4 hydrogens, therefore I'm going to multiply this by 2. 4 oxygens on products, therefore I'm going to multiply my O2 by 2. So this should be the balanced chemical reaction. All right, I think that should be enough time for discussion. All right, so here's what I'm going to do. There are 2 ways of approaching this problem. Okay, one is to determine the limiting reactant first, and then do just one calculation. And the other way is do 2 calculations, and then based on that determine the limiting reactant and the answer. Okay, so after talking to most of you, many students over the years, I know the second method is preferred by most of you. So I'm going to show you that because that's the easiest method as far as I'm concerned, because based on the statistics I have. Okay, so here's how I would like you to approach this. If something works for you, just stick with that. Okay, if not, I'm going to show you the way that's going to work for most of us. All right, let me see. I'm going to clear my doodling first. All right, so one last time. So CH4 reacts with oxygen to produce CO2 and H2O. Right, to balance this, I need to have 2 here and 2 here. We know that already. Okay, now first thing is to make sure that we know what is given. We are given the mass of CH4. I believe it is 320 grams. And also we are given the mass of oxygen. What is it? 960, thank you. 960 grams. And they're asking for the mass of CO2. Is that right? Okay, perfect. That's it. Now, here's the thing. Technically, to do this problem, we need to know the limiting reactant. Okay, if it is CH4, we just run with CH4 because if the limiting reactant calls the shots. Okay, if it is oxygen, we just use only oxygen in our calculation. Now, because we do not know it, we can do two calculations and determine that. All right. So here's how we can do it. Let's assume for a moment that CH4 is our limiting reactant. Okay, so let's start with what is given. We are given 320 grams of CH4. I don't want the grams of CH4. I want to cancel it out. So what I'm going to do is I'm going to divide this by 16 grams of CH4. Okay, because I know that's how many grams we have in 1 mole of CH4. Okay, if I do that, the grams of CH4 cancels out. I'm going to end up with moles of CH4. But I don't want moles of CH4. I want grams of CO2. So I'm going to get rid of moles of CH4. To do that, whenever we have to deal with moles, we need to go back to the balanced chemical reaction. We see that with 1 mole of CH4, I'm going to get 1 mole of CO2. So I'm going to write that down. With 1 mole of CH4, I'm going to write that in the denominator so that I can cancel it out. I'm going to get 1 mole of CO2. Once again, where did this 1 come from? That's the coefficient in front of CH4, that is 1. And the coefficient in front of CO2 is 1. That's how that's where this 1 came from. Ones came from. Okay. Now, if I do that, moles of CH4 cancels out. I'm going to end up with moles of carbon dioxide. I don't want moles of carbon dioxide. I want grams of carbon dioxide. So I'm going to cancel out moles of carbon dioxide too. To do that, I'm going to divide this by moles of carbon dioxide. I know 1 mole of carbon dioxide has a mass of 44 grams of carbon dioxide, right? So if I do that, moles of CO2 cancels out. I'm going to end up with grams of CO2. And this will be, so 16 would be 20. 20 times 44 is 880 grams of CO2. Okay. So that's what we get if CH4 was our limiting reactant. Now, we have to do another one of this. Assuming O2 as our limiting reactant. If O2 was our limiting reactant, we just run with O2. We are given 960 grams of O2, 960 grams of O2, but I don't want O2 grams. I'm going to get rid of that. I know 32 grams of O2 as 1 mole of O2. Why did I do that? So that I can cancel out the grams of O2. I'm going to end up with moles of O2. I don't want moles of O2. I want to get rid of that. So I see from the balanced chemical reaction with 2 moles of O2, I'm going to get 1 mole of CO2. I'm going to write that out now, okay? With 2 moles of O2, I'm going to get 1 mole of CO2. Where did this 2 come from? That's the coefficient in front of oxygen, okay? And then this 1 came from for carbon dioxide, that's, from the coefficient in front of CO2, okay? So when I do that, moles of O2 cancels out. I'm going to end up with moles of CO2, but I don't want that. I want grams of CO2. I know 1 mole of CO2 has a mass of 44 grams of CO2. When I do that, the moles of CO2 cancels out. I'm going to end up with grams of CO2. Okay. And that should be, I believe this is 30. And then this should be 22. 22 times 30 should be 660, right? 60 grams of CO2. Now, here's what we do with this information now. Whatever the calculation produced, the lower number is your answer. So out of 660 and 880, this is the smaller number, so this should be the answer. And the limiting and the reactant that produced the lower number is our limiting reactant. This is going to be my limiting reactant. That's it. I'll give you 30 seconds to think about this, make your notes, ask your questions, and if you have any other clarifying questions, I'm happy to clarify them. Don't even. All right. Questions, concerns, comments do we have at this moment? Any questions, concerns, comments? Anything? All right. So if that is the case, yes, sir. Oh. Remember names one more time. Marcus, go ahead.
Is there any concrete way to determine the limiting reactant right away?
Right away? Yeah, I mean, for a question like this, so you're talking about the second minute. Keep the microphone there for a second, okay? So really quickly, so CH4, 2O2, CO2, 2H2O. So you can ignore what I'm writing for the next 1 minute. I mean, if this makes sense to you and you want to run with that, that's totally fine. So the other method is to determine the limiting reactant first and then run with that, forgetting about the other reactant, okay? So here's how we do that. We are given the mass of CH4. We are given 320 grams of this and 960 grams of oxygen. We cannot deal with mass. I mean, together with the balanced chemical reaction, we need to convert that to moles. To convert mass to moles, we can use this. Mass divided by the molar mass gives us the number of moles. So for CH4, that should be 320 grams divided by 16 grams per mole. And for oxygen, it should be 960 grams divided by 32 grams per mole. Okay, so grams cancel out. I'm going to get 20 moles of CH4 and 30 moles of oxygen. Okay, now this is what we have. Okay, so but based on the balanced chemical reaction, now this is the important part now. Based on the balanced chemical reaction, to react with 1 mole of CH4, I'm going to need 2 moles of oxygen. With 1, I'm going to need 2. With 20, I'm going to need how many, Marcus? With 1, I'm going to get 2. 40, right? We need 40. This is what we need, but we only have 30. This is what we have. So we have less than what we need. Therefore, oxygen is limiting. This should be our limiting reactant. Yeah? And then you run with that.
That makes sense.
Yeah. All right. Any other questions, concerns, comments? All right, if that is the case, let's do this. Okay. I'm going to close this question in 5, 3, 2, and 1. Okay. So melting temperature is all about the ionic force. Stronger the ionic force, higher the melting temperature. And then how do we determine the relative ionic force? The Coulomb's law, and that is the force is directly proportional to the ionic force, okay? The charge product, which is the cation charge times the anion charge, we only care about the absolute value, and inversely proportional to the distance between ions squared. Now, out of these two, the charge product is more important than the distance between the ions, so I'm going to prioritize that. All right. Now, let's do the charge products for these, which is this. Titanium, I don't know the charge, but oxygen, I do know the charge. Oxygen is -2 always because it's in the 6th group. We have 2 of them. Therefore, my anion site must have a charge of -4. And therefore, my cation site must be +4 because we only have 1 cation. Charge of 1 cation must be +4, making the charge product absolute value to be 8, which is huge. Magnesium oxide, oxygen is -2, magnesium is +2. Why? Magnesium is in group 2, that means 2 valence electrons. It's going to give away those 2 to become like a noble gas. Oxygen is group 6, it's going to gain 2 to become like a noble gas. That's why they are forming these charges. Therefore, charge product should be 4. And Ki, iodine is -1 always, potassium is always +1, the charge product is 1. And calcium nitride, nitrogen must be -3, calcium must be +2, the charge product is 6. Calcium chloride, chlorine is -1 always, and then calcium is always +2, therefore the charge product is 2. So, and calcium oxide on the other hand is -2 for oxygen and +2 for calcium. Charge product is 4. Okay, so all of them, not all of them, okay, so these guys D, A, and B have charged products, okay, greater than or equal to calcium oxide. However, magnesium oxide, even though they're the same, magnesium is smaller than calcium, making the distance between the ions smaller. So that means ions are closer to each other in magnesium oxide compared to calcium oxide, making the ionic force stronger. Closer you are to somebody, stronger your relationship, right? The same thing goes with the ions, okay? Magnesium is smaller. As a result of that, magnesium and oxide are closer to each other than calcium and oxygen. Therefore, you're going to have a stronger ionic force in magnesium oxide, making it have a higher melting temperature than calcium oxide. Therefore, those three should be your answers. Let me see if Top Hat agrees with me. Yeah, these three are the answers. What questions, concerns, comments do we have at this moment? Any questions, concerns, comments? I can. Yes, I will. You have, okay. Both of us one hand. All right. So that is that. I have reopened the question. I'll give you 30 seconds more for the next one. All right, I'm going to close this question in 5, 4, 3, 2, and 1. Okay, I'm going to. All right. Oh, let's see your answers first. I have a good feeling about this. Okay. Most of us selected option B, and that is the correct answer as well. Now, the second most popular answer is option C. The problem with C is this. It is true that we have 1:2 ratio. True. However, those are molecules. In option C, they are representing molecules rather than ions. For that reason, option C is out. In ionic compounds, which calcium chloride is not gonna exist in molecules. It's gonna be a network of ions. Therefore, it's gonna look more like B rather than C. Therefore, the best answer for this question is option B. What questions, concerns, comments do we have? So again, the main idea here is ionic compounds have networks of ions rather than molecules. We don't have molecules in ionic compounds. That's the idea concept tested from this question. Yeah. Julia? All right. Now let's move on to the next question. All right, 30 more seconds. Please submit your answers. I'll open the in case you have already submitted the answer for this, I've opened the next question as well. I want to keep this marathon going. So otherwise, I know the phones tend to come out. I don't want that to happen. The mantra for solubility is if the charge product, which is the charge of the cation times the charge of the anion, if it is greater or equal to 4, then it's insoluble, and vice versa. That is the mantra. Okay. All right. I'm going to close this question in 5, 4, 3, 2, and 1. So for titanium dioxide, oxygen is -2. We determine titanium to be +4. Why? We have two negative 2 ions, meaning anion side is -4. Therefore, the cation side must be +4. Okay, because we only have one cation, it must be +4. Okay, that's why the charge product here is 8. It's going to be insoluble. This is up. Calcium fluoride, fluorine is always -1. Calcium is always +2. The charge product is 2. Soluble. Potassium iodide, iodine is -1. Potassium is +1. Charge product is 1. Soluble. Nitrogen is -3. Calcium is +2. The charge product is 6. Insoluble. Calcium oxide, oxygen is -2. Calcium is +2. The charge product is 4. Insoluble. Therefore, these two, the B and C, are the soluble ionic compounds. Remember your name, sir?
Thomas.
What's that?
Thomas.
Thomas, go ahead.
I guess I don't fully understand like A being like 8 and then CaF2 being like 2 and C being 1. Like how exactly does that work again?
So the charge of fluorine is -1, correct?
Right.
Charge of calcium is +2, right?
Yeah.
Charge of the cation is +2 multiplied by the charge of the anion -1. The charge product is going to be -2. The absolute value is 2.
Oh,
Yeah.
okay, yeah.
Charge of the one cation times charge of the one anion.
Okay, so they're multiplied. Okay.
Multiply them,
Okay.
yeah.
That makes sense. All
Wonderful.
right, thank you.
Right. Any other questions, concerns, comments? Okay. So if that is the case, let's move on. I'm going to clear my doodling. Okay, most of us selected those answers. I'll reopen them. I have reopened the question, I believe. All right, moving on. Take diagrams. The goal is to remind you about the ionic compounds, Unit 3, Module 3, so that you're primed to review for the exam when you after this review session. Yes. All right, so apparently I've skipped a question. Which one is it? Is this one? Oh my goodness, where is it? This one. Yeah, this one. All right. So I'm going to close this question in 5, 4, 3, 2, and 1. And here are our responses. Okay, now, calcium chloride, is it soluble or insoluble? Everybody, I need your answers. It's a soluble compound, right? Okay, here's the thing. If the ionic compound is soluble, okay, when you put them in water, it's going to separate into individual ions. Meaning, the correct representation for the calcium chloride in water is none of these. The correct answer is none of them. The reason is you're not gonna get this anymore. What's gonna happen is they're gonna be separated. So they're gonna be, if you draw a box, okay, so you're gonna have calcium ions and chloride ions separated. Okay, so something like this. They are going to be separated. That's it. Something like that. Okay. Anyway, make sure that you count the ions to, mesh them. All right. Any questions, concerns, comments about that? Anything that I can clarify? What questions do we have? Again, this is good. Now, most of us forgot that when ionic compound is soluble in water, they're going to separate into ions. Now we remember. Okay, don't forget that. You just have one day. Yeah? Okay, I hope they won't forget that. All right. Right, let's do. I'll reopen the question for you. Okay, so revise the answers. All right, the big diagram question. I'm going to close this question in 5, 4, 3, 2, and 1. All right, please pay attention for a second, please. I encourage you to collaborate, talk with each other, but when I'm talking, if you can pay attention, I can try to help you. Okay, no. All right. Now we are given this big diagram. Okay, so in this case, we see that mom loves me, but dad hates me. That situation, right? Okay. So the dissolved state is in this corner, meaning it's only favored at high temperatures. All right. So these are the four. I mean, this is the I believe the third option of the 4 peg diagrams. Anyway, now the iron-Watt interactions are stronger than iron-ion interactions. I still see people are not paying attention. Please, can you pay attention for a second? Because it's going to distract me too. I mean, I'm not memorizing them. I'm trying to formulate my thoughts while we're doing this. Okay. So here's the thing: iron-Watt interactions occurs in what state? Dissolved or undissolved? The dissolved state, right? Iron-Watt interactions occur in the dissolved state. Okay, they are telling me that iron-Watt interactions are stronger than the iron-ion interactions, meaning so if this is the case, dissolved state must have a lower potential energy because stronger the attractive interactions, lower the potential energy. But this is not the case according to the Beck diagram, right? According to the Beck diagram, the dissolved state has a higher potential energy, meaning iron-Watt interactions are weaker than the iron-ion interactions. Okay, so therefore, option A is incorrect. If I make a mistake, please let me know. So option A is incorrect. Okay. I'll take your questions after discussing next two, okay? Increased temperature increases solubility. Now, yeah, this is good. Now, dissolved state has a higher potential energy. High temperatures favor the state with high potential energy. Therefore, increasing temperature will indeed increase the solubility. Therefore, this is correct. I like that. Last one. This compound is water soluble at all temperatures? No. So that is the nice corner. That is only reserved for nice corner, right? D is not in the nice corner. It is not favored by mom. I'm sorry, number of configurations. Okay. So for that reason, it's not going to get presence always, but only at high temperatures. Okay. So it's going to be only favored at high temperatures. Therefore, option C is incorrect as well. Okay. So for C to be correct, you need to be like this. D must be in the nice corner like this. If this was the case, then this is true, but this is not the case in the given Beck diagram. Okay. So the correct answer must be option B only. Only B. Yeah, this is beautiful. I was preaching to the choir here. I'm sorry. I shouldn't have done it. All right. Do we have any questions, concerns, comments? I think we are good with Beck diagrams. I'm happy. All right. Let's move on. Oh, I haven't opened them. I opened the next 3 questions. Responses, maybe a little bit more. Okay. I'm going to close this question in 5, 4, 3, 2, and 1. Okay. So here's a way to think about this. Let's count the number of protons, which is the atomic number. Okay. Aluminum is atomic number 13. Therefore, it has 13 protons. Please let me know if I make a mistake. Okay. 13. Magnesium is 12. Sodium is 11. Chlorine is 9. Oxygen is 8. chlorine is 17. Okay. And then the number of electrons. Aluminum, when it was neutral, it had 13 electrons. Now it has 10, 3 less electrons than when it was neutral. Magnesium 2 plus has 10. Sodium plus has 10. Chloride minus has 1 more electron than the number of protons, which be 10. Oxygen is 10 as well. They all have the same number of electrons, but aluminum 3 plus has the greatest number of positive charge in the nucleus because most number of protons in the nucleus. Therefore, aluminum 3 plus must be the smallest, and then magnesium 2 plus, then sodium plus, then chloride, and then O2 minus. Okay. On the other hand, chloride minus has 18 electrons. Why? It had 17 protons. Now it has a negative charge, meaning one more electron than the number of protons. They have 18 electrons, meaning more shells. Okay, compared to 10 electrons, therefore it's going to be hands down the largest ion here. Right, it should be the largest. That's it. Done. Oh, that means okay, all these are larger than magnesium 2 plus. All right. What questions concern? Yes. Oh, there was a lie. Oh, I'm sorry. I skipped one conveniently. Yes. All right. So there was lithium as well, which I skipped. So lithium is above sodium. So lithium, I'm sorry. Let me stick with the same color. Right. So lithium is above sodium because they are the same group, but it has less shells. Okay, so lithium had, I believe, 3 electrons. So atomic number of lithium is 3. Therefore, it has 3 protons. 3 protons, but because we have a positive charge, now it has only 2 electrons. Meaning it has the least number of shells. Therefore, the smallest ion would be lithium. That should be the smallest. Yeah. Why? It has the least number of electrons, meaning only 2 electrons, meaning it has only 1 shell. That should be the smallest. Yeah. So lithium is hands down the smallest, and chloride is hands down the largest. Others are in between. What other questions, concerns, comments do we? Yes, ma'am.
Just
Let me name some.
Kira,
Yeah, go ahead.
do you mind just explaining one more time why the elements after magnesium are larger? Just like real quick.
Oh, so for an example, sodium has only 11 protons pulling on the 10 electrons, right? While magnesium had 12. So magnesium has a greater positive charge compared to sodium. Therefore, those electrons will spend more time closer to the magnesium nucleus compared to sodium one. Yeah. So more protons you have, greater the pull on the electrons, smaller the electron shell. Yeah.
That makes sense. Thank you.
Yeah. So it's about, remember the idea is the electron cloud, size of the electron cloud determines the size of the atoms. Okay. If you compare the atom to a football stadium, the nucleus is like the football at the middle of the stadium, while the rest of the space is determined by the electron cloud. So electron cloud is the key when we're determining the size. Okay. All right. Any other questions, concerns, comments? I'm going to clear my doodling. All right. Oh, yeah. Yes. All right. I'm going to close this question in 5, 4, 3, 2, and 1. All right. Now, one more time, the potential. So please keep this in mind really easily, okay? So the mantra for potential energy has not changed, and it will not change even in term 152, okay? So the idea is stronger the attractive interactions, Joel. All right. Stronger the attractive interactions, the lower the potential energy. That is it. Now, how do we determine the attractive interaction strength in ionic compounds? That's all about the ionic force. right? And again, I mean, we talked about this before. I'm going to talk about this again. So the ionic force is directly proportional to the charge product, which is the priority, the main factor, okay? And then inversely proportional to the distance between the ion square, okay? So we first look at the charge product. If that doesn't cut it, then only we look at the distance between the ions or the R, okay? All right, anyway, for titanium dioxide, again, I'm going to show you how I determine the charge of that. I do not know the charge of titanium, but I do know the charge. I do know the charge of oxygen. It'll be -2. We have two of them. Therefore, the negative side or the anion side has a total charge of -4, meaning the cation side must be +4 because we only have one cation. The charge there should be +4. The charge product is 8. Magnesium sulfide. Sulfur is always -2. Magnesium is always +2. The charge product is 4. Lithium sulfide. Sulfide is -2. Lithium is +1. Always. Charge product is 2. Lithium chloride. Chlorine is -1. Lithium is +1. The charge product is 1. Sodium chloride. Chloride is -1. Sodium is +1. The charge product is 1. So based on the charge product, titanium dioxide has the greatest charge product, meaning the strongest attractive interactions between the ions, meaning the lowest potential energy, then magnesium sulfide, then lithium sulfide, and then lithium chloride and sodium chloride. But between lithium chloride and sodium chloride, they have the same charge product. Therefore, we need to resort to the distance between the ions. So lithium is smaller than sodium. Therefore, the distance between the ions is smaller for lithium chloride compared to sodium chloride. Therefore, attractive interactions between the ions are stronger in lithium chloride compared to sodium chloride. Therefore, sodium chloride has the weakest ionic force, mean highest potential energy out of all these compounds. That's it. Done. What questions, concerns, comments do we have at this moment? Any questions, concerns, comments? Yeah. So the correct answer is, I mean, but what I wrote over here, I'm going to show the correct answer here as well. Correct answer is this. Do we have any questions, concerns, comments at this point? Okay, I say hi there. Yes, busy. All right. Now I'll reopen the question. I think.
I would put it back.
All right, now let's connect that to same compounds melting temperature. Again, this is just to make sure that you make in the links here, okay? So ionic force, how it is linked to potential energy, how it is linked to the melting temperature, right? That's why I kept the same compounds with a different way of asking the same thing. So decreasing means I want you to have the highest melting temperature at the top, lowest melting temperature at the bottom. Highest melting temperature at the top, lowest at the bottom. I don't have to move a finger here. All right, I think that should be enough time for this question. Okay, I'm going to close it in 5, 4, 3, 2, and 1. And here are our responses. The most popular answer, and that's the correct answer as well. One more time, it's the same thing. Okay, so the idea is stronger the ionic force, higher the melting temperature. Therefore, you have the highest melting temperature for titanium dioxide. And sodium chloride, as we saw before, has the weakest ionic force. Therefore, it should have the lowest melting temperature. By the way, the sodium chloride, the compound with the lowest melting temperature, has a melting temperature of 800 degrees Celsius. It's pretty high. All right, I'll reopen this in case anybody swapped them for any unknown reason.
Yeah, I just don't know. We can be good. Phosphorus is the water. Oh, yeah. That's why I didn't know. Why is it? Okay, go that way.
All right, I'm going to close this in 30 seconds so that I can discuss the other one as well. Oh, I feel like I need to get glasses here. It looks blurry to me. Is it the same for you?
Yeah.
Oh, okay. I'm fine. I don't need glasses. Okay. Oh, Matt, I saw a hand over there. Can you run? Oh, specifically, okay. All right, I'm going to close this question in 5, 4, 3, 2, and 1. All right. Before I look at your answers, X has 2 valence electrons. It's in group 2. Okay. Therefore, become like noble gas is going to most likely going to lose those 2 electrons. Therefore, it's going to form +2. So X will form X2 plus ions. While Y has, wait, this is the valence shell of Y. You can see we have 5 valence electrons, meaning to become like noble gas is going to gain 3 electrons. Okay. Therefore, Y is going to form X3 minus. Therefore, when they combine X to neutral, so it will combine in this way. So we need to have 3 X ions combining with 2 Y ions. And then why did it do that? I just swapped the charges. So X is 2 plus. I use that as the subscript for the anion, and then Y is 3 minus. I use that as the subscript for the cation, and that should give us a neutral ionic compound, X3Y2. What questions, concerns, comments do we have at this point? Any questions, concerns, comments? Right, I'm going to clear my doodling. Yeah, most of us selected that. Wonderful. I'll reopen the question.
Excellent.
Showing you the product vessel, okay, or the final state of the reaction, like in a sub-microscopic representation, you are given the number of molecules. It's the same idea though. Okay, they can easily ask the same question by giving you the final state sub-microscopic representation and ask you which one is the initial state or which one is representing the reactant vessel. It's the same thing. Question in different. All right, I'm going to close this question in 30 seconds, so please submit your answers. All right, I'm going to close this question in 5, 4, 3, 2, and 1. And this question is not, it's about counting. Let's see. Most of us selected option B, and that's the correct answer as well. Why? To get 10 NO2 molecules, that means we need to have, so we need to have like at least 5 N2 molecules in the reactant vessel, right? On top of that, you are told that there are 3 excess N2 molecules, meaning you need to have 5 N2 molecules for these guys, 5 N2 for these alone, plus 3 N2s because they are excess. Okay, so you need to have at least 8 N2 molecules, and then the only one, so this doesn't have 8, this only has 5, this is out. This one has 8, 1, 2, 3, 4, 5, 6, 7, 8, this is good. Okay, this one has 1, 2, 3, 4, and then we have 4, that means 8 nitrogens from there, and then we have 1, 2, 3, 4 in NO2 molecules. 4 NO2s. We see. So this can give us how many? We can have 8 NO2s from here, right? If we have enough oxygen. Okay. So, but we just need 4 from here. Oops. 4 NO2 molecules. So therefore, we're going to be left with another 2 N2 molecules because we'll be left over with 4 N atoms, meaning only 2 nitrogen molecules. This is not going to produce 3 nitrogen excess molecules in this. Therefore, this is out. And then the last one is clearing out the answer because you don't have enough nitrogen to begin with. Okay. All right. What questions, concerns, comments do we have about that? Any questions, concerns, comments? Plus, in the reactant vessel, there's no way you can have NO2. Therefore, last two options are greatly out anyway. Okay, because at the beginning of the reaction, you only have reactant molecules to begin with. So there's no NO2 to begin. Okay. All right. Anyway, any other questions, concerns, comments? All right. Last few minutes of our last Thursday of the semester. Oh, this should be easy. We might not get to this, but that's okay. We'll discuss at least the last two questions. All right. I'm going to close this question about temperature in 5, 4, 3, 2, and 1. Okay. And here are our responses. Okay. Most of us say when you increase the temperature, okay, the reaction rate will always increase. Yes, definitely. Okay. The collision frequency decreases is incorrect because collision frequency must increase because when you go faster, you are more likely to collide. That's what happened to my friend. That's why my friend had a higher collision frequency. All right, anyway, because he went faster. All right, the activation energy of the reaction decreases. Okay, this is not true. The 39 of you who selected this, please know there's only one way to decrease the activation energy. What is that? Adding a catalyst. That's the only way. That is the only way. Therefore, option C is incorrect. Okay. So B and C are incorrect. And then average kinetic energy per particle increases. That is correct. Okay. Because when you increase the temperature, particles move faster, meaning you can have a higher kinetic energy. All right. So. Oh, no, this is incorrect. Good. Okay. So anyway, I need to fix that. Please unselect option C, okay? Only way to decrease activation energy is by adding a catalyst. This is not correct. I need to fix that. All right, let's try to let this question. Maybe. All right, and here are responses. Most of us said products have a lower potential energy. Why? Products are all AB or polar bonds which tend to be stronger than AA bonds. On the reactant side, we have some AA bonds. Okay, so therefore we have weaker bonds on the reactant side. Therefore, it's going to have a higher potential energy on the reactant side, lower potential energy on the product side. Okay, and then if that is the case, you are going from a higher energy to lower energy, meaning that you have to release energy. If the energy is released, it's going to be an exothermic reaction. Therefore, most of you selected option E as well, and these are the correct answers. 150. This is pretty good. All right, I'll reopen that as well. I'll remove the last question because we didn't get to talk about this, but you can enter answers, but I'll remove that from the class notes for today. With that, I'm going to give you the attendance code. All right, so idea is to have the best review today. This is the best one you can ever get. All right, for example, of course I'm biased. All right, I'll see you tomorrow, same place. ILC. Yeah, I mean ILC. The UL exam place. Everybody, have fun. You have to prepare and during the exam, have fun. That's the most important thing. Thank you. Hi.
My name is Colin. I emailed you a little bit ago. I'm missing the final for that competition.
Okay.
But I use Sunday. So yeah, and you said to come talk to you after exam 4B, but obviously like I'm not here. So I don't exactly know like what process is. I do really appreciate you being flexible with me because I know
Yeah.
you didn't have to.
So you're leaving Sunday.
Yes, sir.
Be prepared to take the final exam tomorrow then.
Okay,
Can you do that?
I can do
Yeah,
that.
there are a few people, in this situation. So,
Okay.
yeah. So can you email me one more time?
Sure.
So I think I'm gonna send you a room
Okay.
to go to.
good.
You'll be taking the exam there. So you will just after the exam for me, you will take the final exam.
Okay. Sounds good.
What are you calling?
I appreciate
Yeah.
it. Thank you.
Yeah, I'm good. Hi. Yes.